Hello, my name is Eric Rexted. I work at the University of St. Andrews, where we spend lots of our time analyzing distance sampling data, such as the types of data that you'll be collecting in your role as an observer. I'd like to spend a few minutes of your time describing how these data that you will be collecting are analyzed to produce estimates of populations of marine mammals that are of interest to us. To do so, I'll take you through a bit of an idea of how animal populations are censused. How do we go about counting them? I'll contrast censusing of animal populations with sampling of animal populations using a method called plot sampling. And then I'll finally get on to the main focus of this discussion, which is distance sampling, how it's similar to, how it differs from plot sampling. And we'll then go on to conclude this brief discussion with some ideas about how such data, how the estimates derived from such data end up being used. So, the perfect way to try to figure out how many animals are in a population is to census them. In other words, count all of them. And the way we do that is fairly straightforward, but let me explain to you the details. Here we have a study area that in this case happens to be rectangular. And these black dots represent animals in that population. You'll notice that the animals in this particular population are not evenly or uniformly distributed throughout the study area. They tend to be aggregated on this eastern side and occur at fairly low densities on this western side. So, in using a little bit of notation to make our understanding simpler, we first lay out what is it that we're trying to estimate. In this case, the size of our population goes by the notation capital N. So that's what we want to estimate. What we know is the size of the region that we choose to study. So the size of our study area is chosen by us, and so we get to draw lines on a map that says, this is my study area. And so we use the notation capital A to designate the size of the study area, which in this case is simply the height of the study area multiplied by the width of the study area. So we know that's 5,000 units. If we know the number of individuals in the study area, and if we know the size of the study area, we can come up with the density of animals by simply dividing abundance by area. So, complete censuses produce estimates of population size by employing field methods that count everything. Now, you probably, as soon as you stop laughing, you'll understand that this is an easy method from the point of view of analysis, but it's a very difficult method from the point of view of data collection, because most animals tend to be cryptic, or in the case of marine species, tend to spend most of their lives underwater. And so counting everything is not necessarily a trivial thing to do. But if we could develop field methods that would allow us to do that, we would have essentially the gold standard that says there are 412 of these black dots or animals in our population. And then given the known number of individuals, we can compute the known density by dividing the number of individuals by the size of this study area. As I say, hard to accomplish in practice. And so let's be a bit more realistic about what might we be able to do in the field to produce estimates of population size. Notice I've drawn exactly the same study area, same dimensions. I've even used the same population of animals, the same number of black dots, distributed in the same manner. Now, the methodology used in the field is to not count every animal in the population, but rather go to some subsets of the study area and perform our counting there. And by performing our counting there, we hope, by making certain assumptions, that the density of animals in the places that we visit is representative of the density of animals in the places that we don't visit. And thereby, from our sample, we can infer the size of the population. So we proceed slightly differently. We now define the number of places that we visit, the number of plots that we visit, or the number of strips that we visit. In this case, I've denoted those areas that are visited in green. And so we decide ahead of time how many of those places we'll visit. So we know the number of strips. We also, because it's up to us to define it, we also know the total area of these regions visited. So we visit 5 strips. Each of those strips go from the north end of the study area to the south end of the study area, so they're 50 units long. So the total length of transects visited in this particular survey is 250. Note, in addition, that we have defined the half width of these strips. What do I mean by half width? The half width is how far on either side of the strip are the observers, such as yourself, going to look to detect animals. Notice here's an animal that is just outside this half strip width W. And so that animal isn't counted, but all animals at distances less than W from the transects are detected and are counted. So we now have, in addition to the size A of our entire study area, we also have small a area that constitutes the amount of the study area that we visit. Using simple geometry, we multiply capital L times little w times 2, because we're looking on both the left-hand side and the right-hand side of the transect, to derive the total size of the area that we visit. In this case, the size of the area that we visit is 500, whereas the entire study area is of size 5,000. The field methodology is to traverse each of these 5 transects and count everything that we detect out to distance W. That's our field method. By applying that field method, we then come back from the field with the number of animals that we detected when visiting those 5 strips. The question then is, how do we produce an estimate of the total number of animals in the entire study area based upon these 36 detections that we made? Here are things that we know. We saw 36 animals. We visited 10% of the study area. 500 5,000ths of the study area were visited by us. So, assuming that the density of animals in the strips we visited is equivalent to the density of animals in the entire study area, we can use this simple formula that says take the number that we detected and divide it by the proportion of the study area we visited. That leads to our estimate of population size of 360. So now capital N that we use to denote population size, you'll note it has a hat on it. That hat indicates that it's an estimate. We can rewrite this formula to say another way to express a formula for n hat is to say take the number that we counted, multiply it by the entire study area size, and then divide that product by the size of the study area that we visit. We produce the same estimate. So I hope you understand that plot sampling or strip transect sampling allows us to come up with an estimate of population size based upon what we see in the portion of the study area that we visit. So let me break down this idea of plot sampling into two pieces. First of all, how many animals were in the area that we visited? Those green strips that I showed you in the earlier slide. Once we know how many animals were in the green strip that we visited, how do we extrapolate from that number to the number in the entire study area? When we do plot sampling, our estimate of the number of animals in the green bit of the study area we visit is the same as the number of animals we see, because plot sampling assumes that we see all of the animals in those green strips. None of the animals in the green strips elude us or evade us. Given that estimate of number of animals in the green strip, by placing the transects at random, what does that mean? That means every area, every point in our study area has the same probability, has a finite probability of receiving our survey effort. In other words, those green strips are placed at random. They could have landed anywhere. So if those transects are placed at random, that gives us some reason to believe that the density inside those green regions is representative of the density outside those green regions. So if these transects are placed at random, our estimate of total population size is the estimate of the number inside the green region scaled up by the fraction of the study area we visit. I can rewrite it again in exactly the same way I did on the previous slide. So this is the way we produce an estimate of abundance when we do plot sampling. I now want to stretch your minds a bit and contrast the idea of plot sampling that you now understand with a very closely related concept called distance sampling. So again, same study area, same population of animals. In this case, the same number of strips, 5. But now notice something unique about these strips. These strips are now wider. And by allowing these strips to be wider, we now need to take account of the fact that having wide strips might lead us to not detect all of the animals that are in the strips. In particular, animals that are at great distances from the transect line itself, from the dotted line, might not be detected by us, whereas animals that are close to the dotted transect line are likely to be detected by us. So now notice that these green regions are A, wider, and B, populated not only by animals coded in red as having been detected, but also coded in black, indicating that even though they were inside the covered region, the green strip, they were not detected by us because they were at some distance away from the transect line. So distance sampling is an extension of plot sampling, where we no longer assume that all animals inside the green strips are detected with certainty. So we now change the geometry of our samplers a little bit. We now make that truncation distance, W, wider, so that the strips themselves will be wider. And so because the strip width, W, is bigger, then the size of the study area that we visit is larger, because we still have 5 strips, each of them being 50 units long, so the total length of these strips is still 250. But now, instead of them being 2 units wide, they're now 4 units wide, and so 250 multiplied by 4 gives us our little a of 1,000. Unsurprisingly, if the green region is larger, the number of animals we see, the number of animals we detect is larger. And so now we're going to work with this value 68 to try to produce an estimate of the number of animals in the entire study area. However, to do this, we need one new piece of information. I said just a moment ago, we no longer assume that we see all of the animals inside the green region. Some of the animals inside the green region are missed. And so what we need to do is we need to estimate the proportion of animals that were detected inside the green region, because it's no longer 100%. It's some fraction of 100%. And that piece of information is going to be critical to allow us to be able to produce our estimate of abundance. For the moment, let's assume that we know that this proportion of animals detected within the covered region for this survey is 0.7. In a moment, we'll come up with a way to try to estimate that number, but for the moment, let's assume someone told us. So if we know all of the information on this slide, how would we proceed to produce an estimate of population size? A reminder of what we already know. We know how many animals we saw. Someone told us that the proportion of animals seen inside that green region was 0.7. And so the first step in our journey is to produce an estimate of how many animals live inside that green region, given that we didn't see them all. If we only saw 70% of them, then there must be some number greater than 68 that occupy the green region. We produce a number greater than 68 by dividing 68 by a number smaller than 1, 0.7, the proportion that we detect. So this now gives us an estimate of the number of animals that occupied that green region. 97. If we know that there were 97 animals occupying 20% of our study area, where did I produce the number 20%? Well, our little a was 1,000 and our big A was 5,000. So we visited 20% of the study area. So I'm guessing we're going to produce our estimate of the total number of animals in the entire study region by multiplying this number by 5. Multiplying this number by 5 is the same thing as dividing this number by 1/5. So we now produce a new estimate of the number of animals in the entire study area based upon the use of this distance sampling estimator that allows our strips to be wider and also allows us to not have to detect all of the animals inside the strips. Okay. Here's that formula that can be rearranged. This formula looks very similar to the plot formula. It had a little n, a big A, and a little a, and tacitly, that previous formula had a value for p sub a, but it was equal to 1. And so if it was equal to 1, meaning that we saw all of the animals inside those green regions, then we didn't need to explicitly state it. So now that this proportion of animals inside the covered region detected is not equal to 1, we have to include it in our formula explicitly, as we do here. Replacing all of these variables in this expression with the values that we saw in our study allows us to reproduce this formula that says our estimate of population size, given what we know, was 485, 486. So that's a formula for producing estimates of population size from distance sampling when we don't see all of the animals in the study area. Now, you would think we were done here, but unfortunately we're not. We have a pretty important piece of the puzzle that we've not yet resolved. Distance sampling still uses this two-step approach to estimate population size. Step 1 is to estimate the size of the population in the area we visited. Once we have an estimate of the number of individuals in the area that we visited, we extrapolate that to the entire study area. The key to producing an estimate of the number of animals in the area that we visited, given that we don't assume that we detect them all, is to take the number of animals that we do detect and divide it by the probability of detecting them. So that's how we produce our estimate of the number of animals inside the covered area. Given the estimate of the number of animals inside the covered area, we produce our estimate of animals in the entire study area by scaling the number in the covered region by the proportion of the study area we visited. This formula you've seen before on the previous slide. For the line transects, which is what you'll be doing, this little a, the size of the area that you visited, is equal to the total length of the transects that you visited multiplied by the distance on either side of the transect that you observed animals, and multiplying by 2 to take into account the two sides of the transect you survey. So we now come to this mystery creature piece of A. It's something that we have to estimate. How do we do it? Whoops, excuse me. We need one new piece of information to estimate. And this animation is showing you what's happening. But the piece of information that we need, that you need to collect as an observer to make distance sampling estimation possible, is unsurprisingly distances. Distances to what? You need to be able to measure the perpendicular distance, the distance between the animal that you detect and the transect line. And so what we see on the left-hand side of the screen here is an imaginary you on a ship traveling through a study area. And as you travel through that study area, you're seeing some animals that are highlighted in blue and not seeing other animals that remain colored gray. And if you'll notice, for each animal that you detect, there's a perpendicular distance being measured. See those red segments of lines showing up at right angles to the long transect line? So for each of those detections that you make, you're also measuring the perpendicular distance at which those detections were made. What's being depicted over here on the right is a histogram of the distribution of all of those perpendicular distances. Now you notice as your survey proceeds, you're collecting more and more data, you're collecting more and more perpendicular distances, and you're getting a more thorough vision of the distribution of perpendicular distances of detections from the transect line. So this is distance between the animal, distance between sightings and the transect line. So at distance 0, that means the detection was made right on the transect line. And as these distances increase, the probability of detecting animals diminishes. And that is consistent with what we know about how the observation process works. Animals that are more distant from the transect line are less likely to be detected by us than animals that are close to the transect line. And so it is the distribution of these perpendicular distances that you record during your survey that provides us with the necessary information to try to estimate that quantity P sub A, the probability that an animal inside the covered region is detected by us. Okay. So as this histogram is labeled, it's the histogram of the observed perpendicular distances of all of these small distances are being collated into this graph on the right. So after the survey is concluded, you bring back data such as this that can be plotted up into a histogram such as this. Now, what happens to the information in that histogram? How does that histogram of observed perpendicular detection distances help us estimate P sub A? The answer to that question is that imagine every animal that you saw, there was no drop-off, there was no diminishing in the probability of detecting animals, regardless of the perpendicular distance that animal is from the transect line. If that was the case, then our histogram would resemble this blue box. this blue rectangle. In other words, an animal at 2 kilometers from the transect line is just as likely to be detected by us as an animal that is 100 meters from the transect line. Therefore, this distribution of this histogram would likely be horizontal. However, in the data that you collect, the data that you observe, that histogram is not likely to be a rectangle. Instead, there's likely to be a drop-off in the number of detections made at large perpendicular distances, and that the number of detections is likely to increase as you get closer and closer to the ship's transect line. So, the secret to being able to estimate P sub A is to try to do a good job of fitting a curve, in this case depicted in red, fitting a curve to those observed perpendicular distance histogram bars. And so part of the analysis of distance sampling data is to fit a curve that's called a detection function to the observed data represented by this histogram. Given that you've fitted this red detection function to the data, all of the area out here in this red striped region are animals that are missed. They're animals that live at 2 kilometers from the transect line. So they exist there, but you didn't detect them because they're harder to detect when they're far from the transect. And so the region in red stripe represents animals missed, because if this detection function didn't drop off, then you would detect all of them. And so if this area represents animals missed, then this area represents animals detected. We also assume, when we perform distance sampling, that animals that are directly on the transect line, in other words, at perpendicular distance 0 from the transect, are seen with certainty. You see them for sure. If all of those, if you understand the arguments that I made on the previous slide, then this formula represents the proportion or the probability that animals that live within the covered region of your survey are detected by you. The area under this red curve divided by the area of the blue rectangle. So P sub A is a function of this histogram of perpendicular distances that you record. The connection between the histogram of perpendicular distances that you record and probability of detection is moderated through the fitting of this detection function. Okay. So the way in which we estimate the probability of detecting animals inside our covered region is by taking the area under this detection function and dividing it by the area of this rectangle. So it stands to reason that if your histogram doesn't have much of a drop-off, then you are detecting a high proportion of animals inside the covered region. In contrast, if your histogram drops off very rapidly, that implies that you're actually seeing quite a small proportion of the animals that are inside that covered region. And so the key to coming up with a good estimate of this quantity p sub a is the nature of the histogram of perpendicular distances. And so it's critical that those data are recorded well. And I'll talk to you about how to go about collecting data such as that in the next video. To conclude, we could come up with numerical values for the size of the rectangle. The area of a rectangle is simply its base times its height. In this case, 12 times 2. Height was 12. Distance x on the base was 2. So 12 times 22 is the area of the rectangle. The area of under the curve can be approximated by computing the height of this curve at the midpoint of each of these 8 histogram bars. So here I've summarized the height of each of those 8 histogram bars, and I can then calculate the area of each one of these boxes by multiplying base times height. All of these bases are 0.25 because 2 divided by 8 is equal to a quarter, and each of these heights. So in this case, the area under that curve was 17. The area under the rectangle was 24. The ratio of the area under the curve to the area under the rectangle, unsurprisingly, is 0.7, which was the quantity that we used earlier in computing our estimate of abundance. Now, for animals that you study, you may collect data on animals that occur all by themselves, probably not in this kind of habitat, but animals that occur all by themselves, or animals that occur in clusters. And so, as part of the data collection exercise you're engaged in, you'll need to estimate, you'll need to measure not only the perpendicular distance from the transect to these groups, but also the size of those groups. And so that'll be an important aspect of your data collection exercise. The reason I point this out to you is that distance sampling, if you collect data on groups, distance sampling will produce a density of groups in your study area. And to convert density of groups into density of individuals, you'll multiply cluster density by average group size. So, just about at the end of any mathematics that you'll need to know, I wanted to remind you that you'll be collecting data compatible with distance sampling methodology. Distance sampling methodology grew out of, or is an extension of, plot sampling, where plot sampling, everything inside the covered region is detected with certainty, whereas with with distance sampling, we no longer assume that we see everything. And by not seeing everything, we have to come up with an estimate of the proportion of the population, proportion of the animals that we do see, this quantity p sub a. So here you'll get to see the similarity between the formula that we use to estimate abundance under plot sampling and the formula that we use to estimate abundance under distance sampling. The two formulas are exactly equivalent, the exception being that this quantity piece of A has to be estimated for distance sampling, whereas it was assumed to be equal to 1 and therefore not present here in our plot sampling estimator. And regardless of whether you want to report an abundance or a density estimate, the formulas for doing so are very similar. As I've said on the previous slide, the key to being able to produce estimates of abundance from distance sampling is to be able to estimate this quantity piece of A. And we estimate the quantity piece of A by being able to calculate the area of this rectangle, which would be the case if we saw all animals all the way out to the truncation distance W. We take the ratio of that area to the area of this curve under this detection function. And this detection function is meant to be a smooth representation of the drop-off in probability of detecting animals as a function of distance. And the information needed to create that detection function are the histograms of the perpendicular distances that you recorded in the field. One of the other uses of the data that you might be gathering, the distance data that you might be gathering, is in broad scale sorts of enterprises, research endeavors, conducted by organizations such as the Joint Nature Conservation Committee. This group has, over the past decade, been involved, along with us at St. Andrews, in trying to produce distribution maps of marine mammal species around the United Kingdom, waters of the United Kingdom. Information derived from the sorts of surveys that you collect and the perpendicular distance data that you gather allow us to be able to produce large-scale depictions of these animal distributions in UK waters. So enjoy your data collection. Hopefully this has given you some idea of what will happen to those data after they've been collected by you.